Yay!
Yay! Hey, let's play around a little bit with Newton's law of universal gravitation and see if we can calculate some fun stuff. Okay, here it is. Here's the law. The law is that the force of gravity is big G. It's just a constant times the two masses that are involved divided by the distance squared between them. So as you increase the distance, the gravity falls off, right? It's weaker as you get farther apart. And it goes as the square of the distance. So if two things are separated by r, they have a certain gravitational attraction. If you double the distance, then the gravitational force goes down by a factor of 4, right? Because it's squared. If you triple the distance, then it goes down by a factor of 9. And this is just the magnitude of the force. The force is a vector. All right, but let's just talk about the magnitude in newtons. So I'd write it like this. Where big G, remember, is the big G is a constant. It's 6.67 times 10 to the minus 11, and then some units. What the heck are the units? They would be newtons meters squared per kilogram squared. I don't know why you'd want to remember that, but whatever. All right, so gravity is what, of course, holds us down to the Earth's surface. So let's figure out what is the force of gravity between the Earth and a 100 kilogram person on the surface of the Earth. I drew it over to the left, not to scale. All right, so let's figure it out. So the force of gravity is, that would be like 6.67 times 10 to the minus 11. Usually in the calculations, I like to suppress the units because it makes everything just messier. Okay, M1. All right, so one of the bodies involved is the Earth, and mass of the Earth, we know what it is. We'll actually talk about how it is we know that number. That's a strange thing to know how much the Earth weighs, everything on it, everything in it. But we do know that number, so we'll in a later video, we'll talk about how we measure the mass of the Earth. That's a strange thing. But for right now, let's just take it as a known. And it's about 6 times 10 24th kilograms. The other mass that's involved is U. Your mass is, let's say, 100 kilograms, just to keep everything easy. And then, let's put, goodness sakes, that's not a straight line. Let's make a nice straight line. How about that? And then over r squared. Okay. Now, this can tend to confuse students quite a bit. You're standing on the surface of the Earth. So in some sense, you might think, oh, my distance from me to the Earth is 0 since I'm standing on the surface. But what's important is, in Newton's law, the r is the distance between the centers of the masses, the centers of mass of the two things. So the r is the distance between your center, I don't know, maybe that's like a meter up from the ground, and then the center of the Earth. So the meter doesn't really matter that much. But the center of the Earth is a long way away. In fact, the Earth's radius is about 6.4 times 10 to the 6 meters squared. Okay, so always, 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 when you're doing these problems, r is the distance between the centers of the masses. So keep that in mind. All right, well, let's figure this out. Just so we don't have to take the calculator out, can I do something crazy? Can I do this? Look, in the denominator, I have two 6.4s, right? It's 6.4 squared. Well, look, I mean, that's pretty close to 6.67, isn't it? 6.67 is a little bigger. And then there's 6, which is a little smaller. So can't I just cross all those 6's out? There's 2 on the top, 2 on the bottom, and they're all pretty much the same. So just for kicks, let me do that. And then I can totally do that because if I put my little squiggle over here, I can do anything I want. Okay, so now I just got powers of 10. So I got minus 11 plus 24. What the heck is that? That's like 13, right? And then I got 100, so that's 2 more. So that's 10 to the 15th over in the bottom, 10 to the 6th squared. That's 10 to the 12th. So that means that's 10 to the 3rd. That's 1,000. 1,000 newtons. So what I'm saying is the force of gravity between you and the Earth is 1,000 newtons. And then you say, wait a minute. I know that. We've known that for a long time, all the way back to the beginning of the whatever term, semester, book. Because we know that that is equal to mg, right? Where m is your mass, and then little g, that's the acceleration due to gravity. And we had always been saying that that was about 10, right? 9.81 meters per second squared. So if m is your mass, that's the 100 part over here in the calculation. Oop, it's over there. If that's your mass, then all the rest of that stuff has got to be little g. That's really interesting. So little g is really just g mass of the Earth over radius of the Earth squared. That's pretty cool. That's where little g comes from. If you put in the exact values for g, me, and re, what you wind up with is, in fact, 9.81 meters per second squared. So that's where that comes from. That's cool. This also, by the way, is how you would figure out what your gravitational acceleration is anywhere else. So, for example, what is your weight on the moon? On the moon, little g moon is just going to equal to g. You just substitute the moon values in there. It's going to be the mass of the moon divided by the radius of the moon squared. What is that? 6.67 times 10 to the minus 11. You could look it up. I'll just write it down. Mass of the moon is like 7 times 10 to the 22 kilograms. It's like 100th. It's only 1% of the mass of the Earth. Radius of the moon, it's like a quarter of the Earth. It's like 1.7 times 10 to the 6 squared. Okay, you put all that in, and what you'll get out of that is something like 1.6 meters per second squared. So it's like about a sixth of the Earth. So on the moon, you would weigh about a sixth of what you do on the Earth. So you can do this for anything, Mars, Jupiter, whatever. You just put in the right m and the right r, and you can figure out your gravitational acceleration, right? You multiply by your mass, and that's how much you weigh on each of these objects. Cool. In fact, we can do this for exotic objects like white dwarf. Some of you may have heard of a white dwarf. It's sort of the end state of stars like the sun, low mass stars like the sun. It's the burnt out core of the star. So for the white dwarf, they're highly compact, extremely dense. We have nothing like that material on the surface of the Earth. But we have these things that are about the size of the Earth, and they have something like half the mass of the sun packed into them. So could you go stand on a white dwarf? How much would you weigh on a white dwarf? Well, it would just be g times mass of the white dwarf. It's like half the mass of the sun. So that's going to be something like 10 to the 30th kilograms, and it's about the size of the Earth. So that would be like 6.4 times 10 to the 6 squared. When you plug these numbers in, I already did it over here somewhere before. What you get is something like 6 million G's. You weigh 6 million times as much on the surface of a white dwarf. So could you stand on a white dwarf? I don't know. Can you support the weight of 6 million of you on your back? Probably not. That's like an office building, right? So it'd probably squash you flat. So that's just the gravity of some of these objects. So anyway, the point is that now you can figure out how much you weigh on a whole bunch of different objects. Just plug in the right m and plug in the right r. So this is just a sample of how you can calculate the magnitude of the gravitational force between two objects, namely you and some other object beneath you. And then here's one other interesting bit. We were talking before, earlier in the series of videos, or earlier in the course, we said that little g is constant, right? It's always like 9.81. But that's not right. I mean, the mass of the Earth doesn't change, but your distance from the center of the Earth certainly could. So what if you went up higher? If your altitude increases, you're farther away from the center of the Earth. That r is getting bigger. So it makes sense that the farther away you get from the center of the Earth, the weaker the gravity becomes, the less you weigh, right? So when does this become important? Does that mean everything we did in the first part of the physics course is wrong? Well, I mean, yeah, in some sense, but not by much. So let's figure out, just for kicks, when is G reduced by, let's say, 1%? So how high would you have to go, in other words, so that your weight is 1% less? You weigh 1%, you're 1% lighter when you get to some altitude. What altitude is that? So do we have to kind of worry about this stuff when we're dealing with, launching projectiles or throwing baseballs or something like that? Because the ball goes up in the air. And so you want to know, well, I mean, it's a little further away from the center of the Earth when I throw it than when it lands. So maybe I have to worry about that. Maybe G isn't quite constant, right? So let's see. When G is reduced by 1%, here's how you can figure it out. What you can do is you can say 0.99 times G, 9.81, right? That'll be when your weight is 99%, or when the gravitational acceleration is 99% of the usual value. That equals G times the mass of the Earth over your distance away from the center of the Earth squared. So what you can do is solve for that R, and when you do, you will find out, when you plug those numbers in, that the R turns out to be something like 6.42 times 10 to the 6 meters, or like 6420 kilometers. At that distance away from the center of the Earth, then, G has been reduced by 1%. How high is that? Well, look, earlier I've been using a G of 6,400 kilometers. I'm sorry, not a G, but a radius of 6,400. That's actually a little high. It's actually like, I mean, if you want to be more exact, it's something like 6,380, something like that. So the point is that if you go up maybe somewhere between 20 and 40 kilometers above the surface of the Earth, that's the difference, right, between these numbers and the one we just calculated. When you go about 40-ish kilometers high, then your weight is reduced by 1%. So as long as you stay in the 40 kilometers close to the surface of the Earth, what is that? That's like 20, 30 miles, right? So as long as you stay relatively close to the surface of the Earth, then little g doesn't change by much. We're kind of in that 1% realm where we're going to get pretty good answers as long as we keep close to the surface of the Earth. G doesn't change much.